In this video, we're going to explore how the solubility product constant can figure in with Le Chatelier's principle and the common ion effect towards affecting the solubility of that particular compound. We know that solubility product constant in pure water is a way of measuring solubility. But we've also seen that the common ion effect can change equilibria by essentially applying Le Chatelier's principle. We will see, for example, that if we take let's take a solution of 0.01 molar sodium fluoride. Let's try that again, NaF. And let's try to dissolve some calcium fluoride in it. How much will dissolve? What is the concentration of calcium ions in the solution? We see that calcium fluoride has a KSP of, I have it here, 3.9 times 10 to the 11th, negative 11. And now we're going to apply the common ion effect here. So if we understand that sodium fluoride is a fully soluble ionic compound, it's going to dissolve all of it into the fluoride and sodium ions. And so if we want to apply the solubility product constant, we know that that's going to be calcium times fluorine squared, right? Which will be our KSP, fluoride, not fluorine, sorry. And if we take our actual equilibrium, plus 2F minus, we're going to see that we're essentially just starting with a particular concentration of our fluoride. We know that some of the calcium fluoride is going to be dissolving, right? That's the idea. So we're always adding to the product side for solubility product. So we're going to add X, add 2X here. We get X times 0.01 plus 2X. And of course, with this, we can calculate X, right? We can say, okay, we have X times 0.01 plus 2X squared equals our solubility product constant, which is 3.9 times 10 to the negative 11. Solve for X, which I should do right now, so I'm going to pause the video. All right, having plugged those numbers into Wolfram alpha, we get an X that is equal to 3.9 times 10 to the negative 7th power. While that may not seem very important, if we take a look at in pure water, the amount of calcium that would dissolve from calcium fluoride would be 2.1 times 10 to the negative 4 molar. And as we can see here, that's a 1,000-fold difference. Simply by the presence of a common ion, we have drastically reduced the solubility of our slightly soluble compound. So, suffice it to say, generally speaking, adding a common ion generally decreases the solubility of slightly soluble compounds. And this is technically also true for very soluble compounds. For example, if you have a saturated solution of sodium chloride, 5.4 molar, quite concentrated, if you add some concentrated HCl to that, you will actually see sodium chloride precipitate out of the solution. So you do see that you can lower, therefore, even with a very soluble compound, you'll decrease their solubility by adding a common ion, although this is a much more prevalent, mathematically speaking, effect when you have slightly soluble compounds. So when you add a common ion, you just need to do the ICE table again. That's our ICE table right here, of course. And you should see that your solubility will go down. So common ions reduce your solubility, generally speaking, by and large. By contrast, we will see another way of making things more soluble. And we're going to do that in our next video, where we study formation of complex ions.